Okay, let's get started. All right, so as I mentioned last time, finally we are cruising into this exciting territory of deep learning. And the reason I wait until now to address this topic is because, in fact, there are not a lot of new things that you need to know in order to work in this field after you learn all these graphic model foundations. Right, you will see that many of the ideas and methods applied or even invented in deep learning had a deep root in graphic models. I think it's fun, in fact, to see how the stories can be tied together, so that you can actually remember or understand quite trivially a lot of the new methods that has been used these days. Okay, so I'm going to open with a very how shall I say, high-level coverage of the connections between graphical models and deep learning, and then the next few lectures I will invite some of the guest lecturers who are actively working in this field to present some of the basic and the frontier work. Of course, the presentation will be, again, tied to the connection of graphic models and how to really understand, the mechanisms and the rationale instead of just learn how to use it. Okay, so so we were there, and now it looks like the field, at least until last year, is filled with this type of stuff, and to the point that many people, especially the people in a broader community outside of computer science, start to draw equivalence between machine learning and deep learning. So is that really true? Is machine learning all about deep learning? Well, to some degree, yes. But if you dive deeper, you actually will also see a lot of important differences. So I'm going to, again, this deck is pretty long. I may be able to cover the first two parts of the material, and then I leave some additional materials for your after class reading. Okay, let me begin with an overview. So this will be very fast. You all know this already. I want to very quickly pass them and can dive into the foundational part. So the whole business of deep learning study started from earlier historic work in artificial neural networks. And at least one of the most important literature in this field is this paper by McCullen and Pitts, who established a mathematical model over a biological prototype called neuron. Okay, and in neuron, there are kind of concepts, entities known as axon, synapses and dendrites and so on. They actually they are one-to-one mapped to a mathematical counterpart, okay, on the right-hand side. For example, this axon is the output, carries the output of a neuron signal. It's like the electronic pulse. And then these dendrites are the receivers of another neuron. And therefore, it's basically, you can imagine that this is in here. And then, once, and then of course, the receiver and the deliverer are connected by synapses. And then there are this little, entity called I think it's called what is called soma. It's the kind of the neuron cell that integrates the signal. And in here, it is mathematically translated, as you will see in the next slides. And then, naturally, when you look at the neuron, a single neuron in a bigger context, you see a network of neurons. And therefore, likewise, this single mathematical function that combines input and transform them into an output can also be recursively defined into a network like this. And that leads to what is known as the artificial neural network. So here is the mathematical form of that, and also how to estimate key components. You probably already know this very well already, right? So you first have an aggregation function in here that aggregates all the inputs. And this is exactly what's happening in a biological neuron. You have all the impulse signals coming from the inputs. They build up a electronic potential, which is additive. And then there is a gate function, or known as an activation function, which is defined by theta, in this case, a sigmoid function. And they basically are turning into this input signal into an output pulse. And that's also realized in biological system using a iron gate. Once your input is above a potential, they send off a pulse. And then this gate, this aggregation function is making use of a set of weights, so that you can combine a weighted combination of all these inputs. If you want to really understand the biological counterpart of these weights, you could imagine, maybe the length of the dendrites and the axon, the conductance of that, and so forth. They basically are really telling you all signals could be weighted differently, or it could be also weighted identically, but you should treat them as the parameters to be estimated. And then remember that the sigmoid function has a very nice property, which makes the derivative look like itself times 1 minus itself, right? And we actually used sigmoid function earlier in certain machine learning algorithms. Do you still remember what is that?
Logistic regression.
Logistic regression for binary classification, right? And over there, we actually estimate the parameters using a maximum likelihood estimation. And in that case, basically, you are going to estimate the W to be the argmax of this conditional likelihood. A slight difference used in the neural network literature is to define another loss function, which is not likelihood. Well, it is a likelihood, but under a different assumption. Basically, it means that your output has an additive noise, which is Gaussian. Therefore, the likelihood of the output given the input is now defined by this square loss function. Okay, there isn't really a good justification on which one is better, but it's a choice. Okay, so once you are going through this definition, then estimating the weights is very trivial, and I have a simple derivation in here, which gives you a rather nice-looking estimation. Here are the targeted output minus the realized output, and here is the gradient of the logistic function, and this is the input. Okay, and remember, this is to be summed over all observations, okay, of this function. You apply basically this function to multiple coming signals. And if this is really leading to a batch mode learning algorithm, but if you are receiving examples one by one, you have a static version. So these are all well known. Okay, neural network is basically to do what I just said in at least in a operationally recursive fashion. You basically start from the set of inputs, and you define an output, which is a single kind of a neuron function we just defined. And you have another output that can be also defined using a different set of weights. And then these two output become the input of the next stage, and then you get an output, right? So very trivial. If you know all this, you can actually synthesize this kind of network very, very easily. But if you look more carefully into this function, you will find that the actual scenario, okay, of each neuron are different. From it's different from a idealistic McCollum-Pitts neuron as we saw in earlier. Because in these middle layers, you don't actually see the output. This is in a biological neural network. In principle, you could insert a probe and measure the output of every neuron. Therefore, everything is observed. You can estimate those potential and gates and so forth directly using that logistic, not the sigmoid function. But in here, in the artificial neural network, typically you only see the input and the output. You don't actually know what's in the middle. Okay, so that actually is already giving you a key difference. Therefore, people start to ask, is this neural network a model or it's a process? Meaning that it's a process allowing you to fulfill certain computational steps. And here's one way to look at it. At least from the one of the most popular learning algorithm perspective, known as backpropagation, you can actually reformulate or at least rename a neural network to be a computational graph. And for the following reason. Because in this entire problem, what you have is an input and an output. And in the middle, it's subject to design because you don't observe it. But at the end of the day, what you care is the differential of the output versus the input, right? That's all you basically have. It's tangible to you. And we know that these differentials can be expanded using a chain rule. For example, you introduce a auxiliary function or variable. Variable could be a function of some other variables. And then you can basically turn this into this form, okay, versus all possible different values of the auxiliary. And then this auxiliary F1, I1, could also be further expanded into another layer of F2, Fi2. Okay, so this is a computational procedure for you to kind of relay basically the gradient, into different layers, right? And this one, each of the Fi's could well be corresponding to the intermediate layers, in a neural network. And in fact, the way we draw neural network here is look like some graphical models already, at least, right? Symbolically, they are nodes and edges and so forth. I'm going to discuss very quickly, are they really graphical models or what's the difference? Okay. So this algorithm is backprop. We know very well about that. Backprop algorithm is basically a gradient descent algorithm with compounded gradient. And if it's stochastic, you can, of course, make a stochastic version of that. Okay. And by the way, modern versions of neural network packages trivializes this step. You don't actually need to compute all these derivatives already. They have a library of all possible derivatives that you need to work with based on common functions. I noticed that there is a little comment in Piazza or somewhere in a class discussion saying that some of the derivations we show are not actually used. That is true. Nowadays, rarely as a user, a consumer, you derive things by yourself. But it doesn't really mean that you don't want to know how it is derived. In case you invent your new algorithm and models, you may want to know how to do that, right? All right. So now it basically gives you a bigger picture about what the neural networks look like. It's basically, a entity. You could call it a model. You could also call it a computational program or chart that is able to be assembled from a few foundational building blocks. And let's take a look again at what is these building blocks. One building block is this so-called activation function f. It gives you a lot of space for you to define arbitrary, maybe not arbitrary, but your favorite f's. And here I have a few names: linear, rectified linear function, sigmoid, tangent function, many things. Okay. And the next one is the layer. Okay, layer is actually one of the biggest mass destruction weapons, you name it, that you can use to make your neural network really, really powerful. And here, there are a lot of interesting names which are self-explanatory, right? For example, you can come up with a so-called fully connected layer that was historically first introduced. You just have a bipartite graph like this and get them fully connected across the partites. And later on, people start to introduce convolutional and pooling technique. And that's basically look like this. Especially if you have a multi-dimensional, two-dimensional inputs, for example, convolution means that every node in here, in the next layer, is connected to a structured subset of the nodes in here, which could cover a particular region. And then the next node could cover another region, which can be overlapping with this. That's basically convolution. And the pooling function basically is a particular form of the activation, or pre-activation, because the pooled signal still can be further activated. They could take the average of this whole thing, the max of this whole thing, the minimum of that, or a random instance among all these inputs. Again, this is subject to your creativity. Recurrence, can be expressed like this. ResNet, is basically allowing you to connect forward, some residual signals to the next layer. You can basically draw arbitrary topologies, okay, using this kind of intuitive interface. Again, it looks like graphic model. In graphic model, that's exactly what you do, right? You draw topologies. But again, here is the topology modeling anything or carrying any procedure? We'll talk about that later. And then lastly, you need to introduce a loss function, which really connects you or allows you to introduce a task. Say you want to predict a label to build a classifier, and one may want to use a cross entropy, right? If you want to predict a real signal, say in our task of reconstructing pictures, for example, you need to predict the pixel value. You may want to use mean square error and other things. Okay, and at the end of the day, what you do is to bring out pieces of building blocks from here, and pull them together. In all sorts of fancy form. Here is an example of the so-called Google Net, which is a very big neural network. But if you look into that, you literally can find all these components from my library here. Okay, so that's a very good thing because it really, almost like give you a factory of neural networks that you can start assembling, okay, different parts. And you can see convolutions and fully connected and so on and so forth in all different places. And okay, and so that basically gives you, a idea about what the neural network is. It's basically an arbitrary combination of these basic building blocks, and you have multiple loss functions that you can use. In fact, the loss functions can be also combined. You can maybe introduce sub-loss functions internally, if you will, and to make the whole thing more complicated. And there is a myth there, which are widely believed, that this whole thing, okay, which makes the story quite big and complicated, eventually can be trained, meaning that the weights can be estimated if you have enough data, if you keep training. Okay, that's kind of a myth. No one is able to prove that. Empirically, no one is also able to definitively show that, but it cannot work. So also, neural network has a very nice name known as representational learning. And why is that? Because if you happen to have the interest to look into all these little things that is between the input and the output, you actually could find some interesting interpretations out of it, like this. This is literally shown, for certain networks that if you train facial images, and you will see layers like this, with in here it looks like the edges, okay, and in here it looks like the parts, and then different type of faces. And if your input is audio signal, you can see different kind of granularity of the entities, acoustic signals and the words and so forth. You actually probably also always see these kind of pictures very often, right? But if I tell you that very often the whole network may have in this layer a few thousand nodes. And what's shown here is a tiny subset of that. There are other things which are not very meaningful. What do you think? Okay, so the very way of justifying neural network, starting from here, becomes a beauty contest, I have to say, because it's not based on numbers. It reminds me about my good old days about being a biologist, where we pick up the nice examples that we understand and publish a paper. This is very much like that. Okay, I'm not joking. You can train your network because the myth is that if you make the neural network really big, and have really big, large data, you can get it work. But even for physical limitation, you cannot show a few thousand nodes to people, and so I need to pick a few to show. Okay, people literally pick like this. Okay. Anyway, but still, these are very interesting, and it gives you a kind of a belief, and maybe even a intuition that there are ways to extract meta signals from raw data, so that when you project the raw data in space like this, they are disentangled. Okay, they can be separated in some way. All right, so that's basically a neural network at a glance. Now let's quickly dive into a little bit more technically interesting insights. First, let me begin by putting the graphic models and the deep neural network side by side to give you an initial taste about how they related. Okay, so in graphical model, what's the meaning of the representation? Well, it really is encoding your knowledge. You, at least in your mental state, have a picture about how either things are causing each other or they are connecting to each other. Every node has a meaning. Whether it's observed or unobserved is due to the limitation of the reality, but you actually believe such a hidden variable or observed variable exists and carry a physical meaning. And then your edges is really giving you the relationship of all this. So I have a few examples, right? Graphical, directed models, undirected models, and so forth. In neural network, the higher level goal is to learn representations, which may give you ways to enhance the performance. In fact, performance itself is the real final goal of a neural network. You basically measure the whole thing by the end metric, like your classification model is powerful or prediction is accurate or not. Typically, people care less about all these meanings of the intermediate nodes. Only when people ask you why, or tell me the story, they will show you a picture like this, right? These pictures are not really meant to be seriously justifying the application of a neural network. Okay, so that's the first differences. The second differences is that the business of learning and inference. Remember, we spent almost a half semester doing what? Well, we will really literally study different forms of inference and learning protocols. It's an entire business, maybe a good chunk of the business in the research of graphical models. And you see all these names, and also a good amount of work was dedicated to proving the correctness of these algorithms. In deep neural network, this is a downplayed topic, maybe never played or seldom played, because there is a predominantly widely used algorithm known as gradient descent or backprop. Other than that, you don't need to know anything else. That's why in packages like TensorFlow and other places, the inference was not, offered as a space of exploration. You just call a function. The space of exploration is drawing different graphs, designing different architectures, right? So the emphasis become very different. And inference, of course, is become even more trivial. Once you have all the weights, inference is a one pass, from input to output. That's it. There isn't any inference of arbitrary conditional of a node given others and stuff like that. So in that sense, in here, the graph represents a model. And in this type case, the graph actually represents computation. you are basically using those as intermediate states to memorize or to channel or become a conduit of the computational signals or intermediate forms to the next stage. Okay. So that's basically the meaning between the two graphs. Is a model graph is a computing graph. You literally are following, these graphs to do computing. In backprop, you follow the nodes and edge to prop the signal, and the inference you go the other direction. Okay. All right. So what's the utility of these two type of technique? As I just mentioned, you probably can already guess to a great extent how they are used differently, right? In the graphical model literature, the utility of the graph, first of all, it is a vehicle for synthesize the global laws based on knowledge, right? You have a global laws which is likelihood, for example, or regression or whatever, and then this graph can technically help you to define potential functions, local conditional distributions, and so forth. And then you use either the Hammerstein-Clifford theorem or you use the factorization rule to kind of bring them together into a global loss function. And also the graph is really a vehicle to design very sound and efficient inference algorithm because you actually care the accuracy of the inference, right? You want to know, for example, the exact lowest energy state of a piece of metal so that you can control the temperature of a nuclear bomb, for example. How to denote it? That's actually computed in this way, literally. Okay, it's not guessed. And you are not allowed to do experiment very time. I often joke that you don't really design a nuclear bomb by exploding it in your lab on and on. You explode only once. Okay, that is that it's all done. You want to demonstrate it. And in our empirical machine learning community, we do tuning. We basically just fire on and on until it fired right, and then you show it, right? So that's a different way. But why you can actually do this simulation-based design and validation? Well, because you have all these nice, beautiful mathematical forms. You can prove its correctness, okay? And also you can show its correctness by basically, on the one hand, having the ground truth of latent variables, and on the other hand, you have the computational outcome. You compare the goodness and the smallest problem, and you expand to a bigger problem, hoping that they behave the same. It's also a vehicle to inspire approximation. Remember that our loopy belief propagation, right, is inspired by the graph. That it was exact on tree, and then I have edges that is making the graph loopy. I will continue use that algorithm and compute the approximation. In mean field, we remove a few edges from graph judiciously so that they turn into a simpler graph that results in a inner approximation to the marginal polytope and so forth. So you have all this nice characterization of what you actually did in approximation, right? Okay, so that's basically the utility of the graphs, in a graphical model. And of course, it is really a vehicle to monitor theoretical behaviors and accuracy, because you actually could pick out the target and analytically compute or characterize it, and then you compare that with what you see on a real computational procedure. Utility of loss function is a major measure of the quality of the learning algorithm. Okay, the likelihood you have to follow that. Okay. So that's the utility of the graphical model. Let's look at the other side, utility of the graph, okay, the network in a neural network. Well, first of all, it is a vehicle to conceptually synthesize decision hypothesis. That's similar to what we do in graph model in synthesizing the loss function. But here, it's about a decision process that I have to do. Okay, not necessarily a loss function defined globally. So it tells you how to move from the input to the output, synthesize different inputs by different weights, and then how they connect to each other to combine the next layer and so forth. So it's a stage-wise projection and aggregation. Okay. And it is also a vehicle for organizing the computing. Your backprop, your forward inference are literally follow the graph. Okay, and the graph nodes are intermediate states or numbers that you want to compute and store for the next step of computation. You cannot, for example, bypass this graph and start to compute all the values of the latent variables in different places, okay, simultaneously, because that's not going to get you the nice results. And it is also a vehicle to design the stepwise modules of computation. For example, if you have a large model that you want to parallelize, and to avoid generating conflicting collisions, you could divide the model based on the graph topology into some non-interfering parts and then let them carry on independently. There is no obvious utility of the graph in evaluating the correctness of the inference algorithm because we don't know what is a correct inference algorithm in your network. Okay, there isn't a ground truth for all the hidden variables, so people never compare whether two algorithms are generating different hidden layers or the different values of the hidden layers, and I compare which one is better. People don't care. You only care whether the end outcome is generating a good prediction or not. Okay. And the utility of loss function, well, is there a loss function in neural network? Well, there maybe is. Sometimes it's directly as the classification label, but sometimes it's something else, reconstruction error and so forth. Once you train the network, you actually very rarely compare or go back to that loss function to see how good I am. Okay, you actually use the network to do next task, prediction, and so forth. So people usually care less about the accuracy or the attainability of the loss function. Yeah.
So I don't want to get you too far on a tangent, but out of curiosity, more people are caring about interpretability and the correctness of learning algorithms, specifically with deep learning or neural nets. You mentioned, for example, that most of the time you don't actually care about what the intermediate learn. Now, I was talking about a little bit earlier, a lot of people like to point out that intermediate layers do have some features that seem meaningful to a person. So I'm just curious, is there any growing work, or is there any sort of focus?
You will see that. Yeah, this is the opening. There are a lot of coverage of that. Yeah, we're going to. There are new developments which are actually addressing some of this deficiency, but as a community, it is still evolving. Yeah. For example, defining correctness by whether it is useful is philosophically problematic, right? And sometimes truth hurt. Maybe it's not useful, but it's truth. Right. So again, that's a philosophical debate. Let's push aside. Let's first get a good understanding of what's happening in here. So that's a comparison that you can digest a little bit more. And now you probably already have your initial answer to that. Are these two the same? Machine learning and the DL the same? Well, probably not. They have some kind of shared goals, but they have a lot of differences in exactly the philosophy behind it, the execution and all that. And in fact, even the vocabulary, this is something I found to be least necessarily different, but they are. And that causes a lot of confusion. If you look at the literature of neural networks, people in there are very fond of having fancy names. Okay, instead of calling something a variable, they call it a neuron. And instead of calling something a content function, they call it an activation function. And later you'll see even better, even more interesting words like sleep, awake, and a lot of other things, right? So that's very interesting. It sometimes creates a how should I say a cultural barrier because the newer readers start to lose the connection of that piece of work to the history because the naming become different, right? But if I honestly tell you that, hey, this is after all, BD propagation or gradient descent, okay, you may actually be able to trace back to earlier history and find new literatures talking about this and end up benefiting you with more ideas. Anyway, I'm going to, in the next few lectures, build a unified vocabulary to at least show you some of the key concepts, are well connected to what we already know. Okay, so far I think we know what is the differences between a graphical model and the neural networks. Okay, and but after all, these two community has very, very deep connection. There are some neural networks which could be just understood as a proper graphical model at the very beginning, and later got a divergence into different application use cases. So I'm going to review some of these cases, and also at the same time gives you what is the mathematical insight behind it, so that you can use the same knowledge to help you understand other networks. Okay.
In neural networks, the prediction part is, why do we call it inference? We're not learn. Is that, do we learn?
Why we call it inference? You don't have to call it inference. Okay, that's fine. Just like why machine learning call prompt estimation learning, it's just a flavor. I think it's a characterization of a computing, that you want to compute the value of a node, and typically we call it inference. Okay, you can call it other things as well.
Is it learning? Are we outputting a distribution which is outputting a single value?
You will see. Okay, and you probably already have the answer. Do people call their neural network a distribution? Right? No. Yeah, that's why I say that a neural network is not a model. It's a graph of computing. Okay, it's not a model in most cases. But in reality, it can be a model. It's just like people ignore the modeling part of that, and I don't care about the correctness of that. I only want them to be a micro or a vehicle to carry the mechanical procedures of computing. That's how people use it. It's like you buy a SUV which is meant to drive in the rough land, but I can still drive it in a good city and enjoy it, right? So that's just you use it the way that is not meant to be, maybe at the beginning, and later on you find a bigger space to develop new applications. Right? Okay, so let's begin with this very modest model. You've seen it before, right? It is a two-layer undirected graph model. There are names, different names. Physicists call it a restricted Boltzmann machine, and for graphical model and statistician people, we call it what? A macro-random field, right? And here is the joint distribution. It does have a proper distribution, and one visible layer, the other is a hidden layer. And how to learn this model? Well, we can properly write down a loss function, which is marginalized over all the hidden random variables, and we're going to take a derivative of that with respect to the weights. And you should be able to come to the right-hand side of this equation. It gives you two terms. Okay, one term is a expectation taken on the conditional of the hidden, given the observed. The next term is the expectation taken on all random variables, hidden and observed, over something. Okay, you probably remember that in our one of the classes talking about the learning in indirect graph model, even the model is fully observed, you still need to infer the distribution of the observed random variables in the learning phase, and that's actually already giving you a phase. And this is known as, in fact, there are fancy names for these two steps, okay, even though they look rather similar, at least from a statistical perspective. Okay, over the posterior and over the joint. All right, look at this again. So how do you approximate this expectation? Well, you could approximate them using a technique we just learned, sampling algorithm. Right? We can, of course, there are other ways to approximate that. That's use sampling in this case. So you can sample from this distribution and sample from that distribution, and then compute this expectation. And the first step amounts to sample from the posterior. Okay, you can do it exactly. It's very easy. Why? Remember, we have nice properties in graphical model, especially on deseparation and the conditional independencies. The graph looks like this, right? And this is observed. In a undirected graph model, when a common kind of neighbor is observed, all others deseparate, right? Therefore, you can sample the node one by one, which is pretty trivial. Okay, that's a nice thing. So people consider this step to be easy. Okay, the next one is non-trivial. because now you are not allowed to condition on anything. You basically need to sample the whole distribution. Okay, and what do we do? Okay, then that opens up a whole literature of inventions. And again, inventors like to give their inventions fancy names so that they are more memorizable. The first term, for example, was called the following names. It's called the clamped, which kind of makes sense, right? Because it's clamped. Next one is called the weak, which is a little bit less intuitive. It's mysterious. Positive maybe means it's easier. And then the next phase, you need to, okay, why we want to sample from Gibbs in here? Well, Gibbs basically gives you a way to mimic what's happening in here. You could, for example, first draw a random sample from here, and then draw a random sample from here, conditioning on the first, and then you can draw the next condition on the other part. It becomes iterative. Then it looks like sampling from a posterior. But it will, of course, iterate many, many times until convergence in the Markov chain. It's a little bit more complicated. But it's still computationally feasible. Okay, so the next, this particular step, for some reason, is called unclamped. Yeah, of course, they are not observed. Sleep, free, and negative. And in fact, you have, there are even other fancy words like dreaming and other things invented. Okay, so you can find this in Hinton's paper, talking about a algorithm in Science a couple of years ago. I'm going to talk about why they are called so in another lecture. They actually are quite interesting and insightful, but that's not today's focus. They actually connect very deeply to the now GAN models and the variational autoencoders. Okay, they actually are not too much different from those models, even though they are 20 or 30 years earlier. Okay. Anyway, let's go back to our major topic. We basically want to understand that learning this is possible. Okay, using a MCMC, especially for the second phase, you can do iterative MCMC Gibbs sampling based on one slide given the other and so forth. And of course, there are convergence issues about that. That's not the focus of today's topic. Let's see how that inspires to other more kind of familiar models that we see in neural network. So let's see another model. Remember the first one, I'm going to put it on shelf for now and then revisit it very, very soon. The second model is known as a Sigmoid belief network. In its basic form, it's very easy. You have nodes as input. You have another set of nodes as output. Now it's becoming directed. Okay, and in some of the earlier work of medical diagnosis, this work was widely used. These are the input as symptoms, temperatures, and all sorts of things that the patient may have. And this is the output or diagnosis you want to make. And I combine them with a sigmoid function. So very trivial sequence. You can also make it a multitask by multiply predicting different symptoms. Okay, or different diseases. That makes a network topology. But the performance was not very good. Okay, because in the sigmoid network, what you really have is a linear combination of all the signals, then plus a threshold. Some interesting interactions between the variables are not necessarily additive, right? They may be, subtly correlated or influence each other in a nonlinear fashion. And without introducing nonlinear function, but achieving a nonlinear effect, what people do?
Hidden layers?
Hidden layers, yes. That leads to this kind of stuff. One hidden layer, multiple hidden layer, and interleaving hidden with observer can do all sorts of things. But the key part is that everything is connected using a sigmoid function. Okay, so that's known as a sigmoid belief network. It's a big business. It actually starts to look like a neural network because at least now you are free to compose all different things. And these hidden layers, do you really care what they are in terms of the intermediate meaning? Maybe not. I just care some kind of intermediator, right? So syntactically, it is still a graphical model, but operationally, it starts to deviate. Because you care less about what is exactly those hidden layers, they become a stepping stone for you to reach a decision. Okay? And all you need to know in terms of the local function is this guy, which is a sigmoid function. Of course, if you want to treat it as a graphical model, when you train this model, there are some practical difficulty because now it is connected at the bottom and it is connected through direct edges. You have this explain away phenomenon. What's the consequence of that? It means that whenever you want to infer any particular hidden random variable, it's coupled with all other hidden random variables, okay, in that layer. You could have thousands of hidden variables. Suddenly, they are all coupled. This is very different from our previous RBM, where the D-separation allows all the hidden variables to be independent of each other given the other layer. Here it's the opposite. They got connected. Therefore, inference here is very, very inefficient if you want to treat them as a series graphic model. And you don't have to, okay? You can actually treat them mechanically as a computational vehicle. That's the story I'm going to talk about. Okay, so we have two networks. What's that? It's directed, it's directed, right? It's sigmoid, and you define pretty explicitly the input and output, right? And input points to the output. And again, just to convince you that it is indeed very complicated in inference, I did, I copied a few steps of derivations of that gradient. And without going through that, you can actually see that in here, the conditional of one random variable given others, given the observations, everything is actually requiring you to tie together all the other random variables. Okay, so this is a program where there is no negative phase like the RBM, where you enjoy simplicity. Convergence is very slow. Okay, all right. So why these two stories has to be brought together? Okay, so that's a interesting kind of a leap of faith. Okay. That hopefully you can now appreciate. So we look at again the inference or the gradient of the RBM likelihood function, and let's think about how to. Okay, I lost my beautiful graphs in here. That's terrible. This meant to be something that is really, really important. Let me see whether I can bring it back in another way or not. Because I prepared the slides on Mac, and now I'm showing the slides in PC. And I'm worried that it will really, okay, here at least I have something. I have something here, okay. So it's only these 2 pages. Okay, I have another idea. Let me present you the PPT or the PDFs of this page. At least you'll see what I meant. Okay, this is what I meant. Great. All right, so let's think about this particular step. And I said that you can sample the joint using a Gibbs procedure, which basically alternates between different subsets of random variables. The vanilla Gibbs is asking you to sample every single random variable given all the rest, and you just cycle through all variables one by one. A broader idea is called the block Gibbs sampling, where you just group the random variables into arbitrary blocks, and then you sample every block given everything else. And here I'm going to group the random variable into 2 blocks. One is the top layer, the other is the lower layer. And then my procedure is like this. I begin from somewhere, maybe from the observed. I basically just introduce my observed variable. Okay, which is given as the input. I'm going to sample the hidden. And then given the hidden, I'm going to sample the output again and go this forever. Okay, so that's basically a very natural Gibbs sampling step. And all I need is these two conditional distributions, okay, v given h and h given v, which are both what? Sigmoid functions. Okay, so if you look at this, that's actually very interesting. If you just look at a particular step like this, okay, I couldn't draw it here, unfortunately. You can imagine I draw a box here. What does it look like? It's a Sigmoid belief network, right? What you are doing here is really to sample from a particular step in the Sigmoid network on and on, okay, many times. So, in a sense, we are now, you can think about the Gibbs sampling, from the joint as, a top-down, propagation of what we know as infinite layers of Sigmoid network, because every pass of this is basically a Sigmoid network, okay, from a input to the output, and your one episode of the sampling is actually breaking down into concatenating multiple sigma functions, and you sample every time just once from that network. Okay, now I'm done with these slides and go back to here because I can draw it in here. So here is a graph showing you what's happening. You have this and you do alternating sampling, and this is equivalent to really, this same sampling procedure from this graphical model. What I showed in the previous slides is actually these slides, okay? But in here, in every layer, you have the weights, and they are the same to each other, okay? They are the same weights, in here that you imagine you see, either from the V of V to P or H and H to V. So we have two sets, W and W prime. But in every, layer in this infinite stack, they use the same weights. And then sampling, one pass, sampling, a epoch or a episode from a Gibbs sampling is basically a one pass of this infinitely many layers. Okay. And remember that if you have a layer, okay, so sorry. If you have say a network stack of infinite layers, let's say this is infinity, then how about I chop away two layers and look at this? How many depths? Infinity minus 2 or minus 1, still infinity, right? Therefore, this equals to a RBM, and this also equals to a RBM. Okay? Therefore, you can literally just do the following. So this one, equals to a infinite, network of Sigmoid beliefs. Then you can basically just leave one layer out and call the remaining layers also the RBM, and likewise in here, and likewise in here. Okay, and this is actually going to be very interesting because you actually see a correspondence between a proper graphical model, which you can learn using a proper algorithm, now into another network, which you could use in one pass from top to down. Okay, they are equivalent. Okay, learning or inference in this model is equivalent to a one pass procedure from this network. Okay, and then it gives you an idea about how to train these neural networks. Okay, in the training, what you do is that you just could sample infinitely often from here, which literally allows you to really keep updating the weights. And this updating of the weights in the RBM in both the forward direction, which is h to v, and the top-down direction, which is v given h, these are the two sigma functions, is equivalent to learning the weights from an infinite stack of Sigmoid belief networks, except that now their weights are clamped. You only basically are using shared weights in here and in here and in here. When you go top, we'll go from h to v, and alternatively from v to h. Okay, so just to wrap up, the connection between RBM and the sigmoid is that the RBM is equivalent to a sigmoid network, infinite depth sigmoid network with all the weights clamped or shared, okay, across the layers. All right, so in fact, what we just showed here, this, of course, was an afterthought. People recently looked into, in fact, Rafael Neer, he looked into this and discovered this equivalency. But other people who didn't know it actually designed a model which is really literally look like what we just showed. It's called the deep belief network. Okay, the network goes like this. It's a hybrid model with a layer or multiple layers that is a RBM. Okay, and then they connect to some observations or latent variable through the sigmoid network. It's a combination. Okay, so technically in the graphic model literature, they are called chain graphs. And again, people know it is pretty difficult to learn because of these explain away effects. But it is pretty easy to define because you can really write down the joint using this thing is RBM, and this is a sigmoid network, and this is a sigmoid network. Okay? And how do you train it? Well, you train it by maximizing the likelihood function, but as I said, you have challenges, due to the explain away effect, so that the training isn't very, very trivial. Okay? Now that you know the equivalence of the RBM and the sigmoid belief network, here comes to a heuristic that people start to find useful. So I'm going to use a stage-wise technique known as layer-wise pre-training, okay, which goes like follows. I'm going to train, let's say, so the idea is that you pre-train and freeze the first network like this, and then you stack a network on top of it. Okay, so for example, you have this network, you trained it already, okay, using your alternating wake and sleep algorithm, as I mentioned before. Okay, and then once you train it, you are going to now put it there, and you have this particular layer of nodes already observed, because you can sample it from this trained network. And then you stack another network on top of it. You start to train this one. Okay. Once you train this one, this node become observed, you train this one. Okay. And why this is equivalent to the deep belief network? Because every one of here corresponds to basically an infinite layer of sigmoid networks, or a combination of some layers of RBM plus some other layers of belief network. So mathematically, they are equivalent, right? What you really are, really getting back through this layer thing is a computational procedure that you make progress on this first, and then you make another progress on this first, and then you are going to now go, layer by layer up until you get, enough depths that you are happy with. Okay, so let's just take a look. You say start from the layer 2, and you put it there, and this layer 2 function you just trained is equivalent to basically this network, okay, with all the weights tied to W2 or W2 prime, okay? Then you are going to now, reduce it to the RBM representation. You make this node available, and you basically train another stack of RBM, which basically is, if you see here and here, what is the difference? Because just to make it, this is a little bit tricky. I want you to really, really appreciate it, understand it. This part, W2, okay, is equivalent to this, okay? And this one, the W3, is equivalent to this. Now, if you look at this graph and this graph, what is the difference? Yeah.
Number of directed layers.
Well, we're talking about the infinity. Therefore, basically, go above, you can go infinity. So the number of layers isn't really
The direct layers.
direct layers. Well, no, they are all infinite, right? Yeah. Look a bit more carefully of my notation in the graph. When I say I train RBM2, and then when I say I train RBM3, what has been changed? Right. I'm basically allowing now in this infinite layer, certain layers of weights to be updated, but not everyone, okay? So in here, what's happening is that I allow all the weights above the top layer, above the bottom layer to be updated because it is equivalent to this single, RBM, and learning the weights of RBM in here is equivalent to learning the weights of all these layers in the infinite stack of sigmoid, right? Now that I put the RBM2 here, and I put RBM3 on top of it, that means that in here, the W2 from RBM2 is now fixed, but I allow everything above to be changing according to the W3, okay? So I declamp basically the weights, okay? If everything is the same, then this whole stack is equivalent to a single RBM, right? And now I use this trick of a RBM is also equivalent to a subset of the infinite stack to retrain the weights. Okay, so here is basically becoming a computationally motivated procedure. I'm going to allowing myself to incrementally go more and more layers of weights. Remember, the very definition of the deep belief network is what? If you remember the topology, the design was like I started with RBM and I have multiple layers, finite layers of observation of sigmoid networks. And my question was how to train that. Now, okay, this is how I train it. I'm going to use this infinity equivalence to allow the weights to be gathered or trained step by step. Okay, until I get to maybe W5, that is corresponding to my original 5-layer deep belief networks. Okay, you are confused because you come from the graphic model lecture. You find it's pretty unnatural, right? It's right, it is unnatural because we don't know what we are doing. we didn't really ask what is, dogmatically you should say, okay, I have a 5-layer deep neural network, deep belief network, and there is a hidden position layer at the bottom. Let's define a loss function on that, and my algorithm should be optimizing the loss function and so forth. Now, we didn't even talk about the loss function anymore. We talk about a procedure which allow me to train this first, train that next, and train the third one next, and then give me 3 sets of 5 sets of weights. Are they optimizing my loss function? I don't care. Okay, I just get 5 sets of weights. I tell you, this is one of the core methods in neural network. Okay, you start to worry about procedure more than the loss function. And then once you get the procedure right and you have all these weights, then you start massage it. Okay, further tune it in its neighborhood until you have a satisfactory performance, which is performance is really about why do you build this network? Even that you want to build this network for classification, then let's worry about classification. Let's not worry about whether they maximize the likelihood of the input and so forth. Okay, so that's the idea. You basically are using, this kind of a connection, to, RBM to kind of help you justify, a computational process, and then you copy that process to, a finite layer model, and get your estimation, which hopefully could be an approximation to some truth, although we don't know the truth. And then comes to the follow-up story. You have now these layers. Imagine that you are pre-training every stack like this. That's exactly what people do in the unsupervised learning. You have the input image, you pre-train a network, and you stack on top of each other. And this is done in a greedy fashion, layer-wise. And to get the whole thing work, okay, to make this whole thing work, you do another step called unrolling. You basically are putting the same network upside down on top of here, copy the same weights, okay, so that you start to have something called an autoencoder. What is an autoencoder? Again, it's a fancy name, but it's basically a two-phase neural network. You can call it one phase. Basically, you put the input to the output and ask the network to regenerate itself. That's known as autoencoder. And now this neural network isn't starting from ground zero, because it has all these weights pre-trained from little blocks already. Okay. Then what do you do? What you do is to do the so-called fine-tune. Fine-tune is that now that you have an autoencoder, therefore you have this output already being observed, and that causes a fully legitimate neural network with input and output, so that you can define derivative from the output and the backprop the signal, right? So those backprop signal will be used to augment those these pre-trained weights, okay, to get to a state where maybe the reconstruction error is minimized. So now let's review, right? You started from a RBM with this as the output, and theoretically you have a proper inference algorithm which allows you to iterate and get you to a convergent estimation of the W. But you are not happy because I give you only one layer of W. You are going to have another layer which basically are trained the same way, although the output was using the kind of the other the hidden variable realizations from the previous RBM. And you do this a couple times, you get a set of weights, which is now not guaranteed. In fact, they are not optimizing anything, okay, collectively. Then you stack it head to tail again to create an autoencoder, and you change the loss function now to a reconstruction loss of the input. And then you use that to jumpstart a backpropagation, which is again a computing procedure that showers the signal to every hidden variable in the middle layer, and they are going to augment it, and you converge. Okay, so up to this point, you should realize that a deep neural network or a neural network of different forms, the biggest emphasis is, first of all, a operationable and hopefully legitimate computational procedure that allows you to get the necessary numbers, like the weights. And then there is also a final task that you want to make sure you understand. In this case, a reconstruction loss. And sometimes the reconstruction loss can be further replaced by a regression loss or a prediction loss, so that you can further augment it. Okay, because this one is not even a final spot. If you want the network to do directly a classification, you could add another layer in here and put a label here and further do backprop. That's possible. Okay. All right. Now you can imagine there are even fancier, or maybe wider connections. For example, there is another model known as not the RBM but the BM, the Boltzmann machine. Okay, without restriction. That means a macro-random field of arbitrary layers of depth with the bottom layer to be observed. Yeah, you can equivalently learn this network using the stacking technique I just mentioned. And in the early days of neural network, these are the deep learning algorithms and models people built, which is at that time consciously made to approximate a graphical model, okay, to simplify computation. And also people kind of know where the simplification happens and where an approximation was introduced. And later, of course, people go, because all these neural networks, all these deeper graphical models are not very powerful in terms of their performance. Okay, they get you something, but not as powerful as the modern era neural networks. But it's a good idea that inspires people to go a lot deeper, and wider when GPUs and other computational machinery and resources become suddenly available. Because here, you basically can directly benefit from bigger machinery. The complexity of learning and algorithm here is linear to the size of the graph, right? You only care about backprop, stacking, and all that. It's not about doing exact inference where tree width and other things start to influence the quality and the cost. Okay, so let's go back and wrap the story together. I will give you some more insights and before we close today's class. So here are some critical points to note about these models. The primary goal of the deep model is to represent the distribution of the observed variables, and usually adding layers of hidden variables allows you to. I should really say this one is even questionable. It's not necessarily the distribution of observed random variables. It could be just the predictability or the generative mechanisms of that. But it allows you to really have increasingly complex, representations in the intermediate to make the distribution more complex. But the hidden variables, are secondary mechanisms to facilitate learning in a deep learning setting. And the training the models is usually ad hoc, okay? And the quality of the learned hidden variable, I think the virtue of that is not about how accurate you can learn it. It's really about how useful these hidden variables are in terms of boosting the final performance. And the representation are judged by their usefulness in the downstream task, not by the recoverability of the ground truths. Okay. Classical graph models have their own sets of virtues and priorities, especially focusing on correctness of learning and inference of all random variables. Okay, given time limitation, I want to skip this. This is an older study I did many years ago when I was a student, comparing basically how wrong people can go, in applying a trivial algorithm for a deep neural network. Okay, that basically gives insight about the mathematical correctness of all these backprop and other algorithms in deep network. And but despite those incorrectness, it could work still empirically. That means there are some other topics that you want to talk about, study, in justifying this type of models. I think the next thing is particularly interesting that I want you to know. What's the connection between deep neural network learning versus optimization? Okay. Sometimes you'll hear now a new term called learning to learn, right? And you probably heard about it. It's a mysterious thing, but it's very interesting. Actually, that kind of gave you an insight into what's happening here. So we see the connection between deep learning models and the graphic models. And we also know that we can treat it the process of learning deep network weights as equivalent to first learn a model with infinite layers, okay, of neural network components, but with clamped weights, and then we declamp it, okay, and then optimize each layers of weights. So remember this, many network and go this and that way, alternating this, right? So what's happening here is really you are unfolding a optimization algorithm, imagine that you have a gradient descent algorithm, which will optimize the parameters in a space, which requires you to do gradient descent or to do whatever descending algorithm. And typically what we do is to keep running the algorithm until convergence. And the theory says that once you go infinitely many steps, you will be converging somewhere here, right? And that's exactly corresponding to what we should do in learning a RBM. In learning an RBM, remember, basically, these are RBM. If you sample them iteratively, from V to H and H to V, it really corresponds to, having infinite layers of RBMs like this, and you have one pass of that, right? So are we on the same page in here? Learning a RBM, using GIP sampling translates to a one-pass algorithm of these infinite layers of networks, but then with the same weights, right? What's realistically happening is that I'm going to truncate this into finite layers. This is like in here, I'm going to not going to the end, but truncate, like stop in step 5. And then I'm going to now allow the weights in here to be untied. And how to untie it? Well, I'm going to learn every of the weights of every layer separately using a pre-training type of technique, in whatever technique. It could be still iterative, and converging to some local minima and so forth. So what is that? What does that mean? That means that once you truncate here, say I want to only learn 5 steps, okay, rather than infinite steps, then in every step, I'm going to do a lot of further optimization, okay, to get the best possible steps. Okay, therefore, originally I'm going to get one set of weights in this model, and here I'm going to get 5 sets of weights in this particular model where they are not going to be, basically corresponding to the same weights anymore. It's a kind of a weird story, so maybe I give you one analogy, which may not be quite right. Say I want to climb to Mount Everest. I want to build a railway there. It's kind of crazy, right? I want to build there. And I imagine I need to take this gradient ascent step infinitely until I reach to the top. Okay. But while I'm working on that, I'm going to change my goal a little bit. Maybe I should come from Naples to the base camp. Okay, I will stop here. And how many steps it took me to go there? Well, maybe there are 10 segments of railways I should go there. I'm going to only build my railway there. And then I go back and rebuild every segment of that railway. Okay, and build it into perfection. Say it gets me the fastest in that segment and in that segment and in that segment. So look at these 2 tasks. They appear to originally have the same goal. I'm going to Everest. I want to build a railway all the way here, and the way I build is I build segment after segment. But then suddenly, I change my goal to be stopping in the base camp, and I go back and rebuild my segment to its perfection. The purpose becomes different, right? It's not going to the top anymore. But you can still claim that there are some utility. Maybe some other people are just coming here for a tour. It's not going to climb. And they can benefit from this task which were motivated originally in a different goal, but now serving a different purpose. And that's basically about optimize or learn to learn. You are now learning. Originally, the entire pathway of railways to Mount Everest was your kind of a learning course. Now I'm going to learn, meaning that I'm going to optimize the way I learn. Okay, or figuring out how to best learn. Maybe a part of that. Therefore, every segment gets rebuilt, and that's basically what's happening here. Okay, so that's the connection. Every deep neural network could roughly be mapped into, a proper graphic model of some form, but you are using this deep network to document the computational steps you use to learn that ultimate graphic model. And now you are going to treat the computational steps as the goal itself and start to optimize every step, which is the weights in every layers. Okay, and at the end of the day, you may forget about what is the ultimate graphic model anymore. For example, people don't worry about RBM in this case. You are going to worry about these finite layers of sigmoid networks with unclamped or different weights, and they may be used for other purposes, maybe a classification, which is not the same as RBMs. Okay, so that's roughly people start to realize that you actually could understand a neural network in this way. You are really truncating optimization and start to optimize every steps in optimization, and that leads you to a network. And this, remember, is not giving you a graphic model. It gives you a computational graph that allows you to optimize the computational graph itself. Okay. All right. And if you, in fact, this technique has been used to extrapolate and empower previous trivial algorithms or maybe classical algorithms with additional layers. For example, we know RBM, CRF, which is the two-layer version of for natural language applications, right? And now it's called a structural output because the output is not a label but a sequence of stuff. And you can just extrapolate into this, and you have this whole stuff in the middle, which could be layers of however connected hidden variables. Okay, and what's achieving is really, you are really trying to get a CRF which is kind of augmented with the computational steps in every layer, fine-tuned into a local goal. Okay, at the end of the day, whether it is solving the original CRF or not is depending on how you tune it, but that gives you a different space of optimization. That's why people sometimes call the deep learning algorithm, at least, as a instance of learning to learn. Okay. Okay, I think I'm going to stop here just to close the very first introduction of DL and GM relationship. They are similar at the very beginning, which has structures and energy term, nomenclatures and terminologies are also similar. But at the end of the day, they diverge, okay, with a lot of different technique and also especially a lot of different philosophies behind it in driving the utility of all these different applications. Okay, with that, we're entering the spring break. I hope you have a great break, but I also hope you can take some time to start reading some of the posted papers in this domain, which is quite interesting. In the next few lectures, we're going to discuss building blocks of deep neural networks with properly motivated statistical principles and deep generative models that explains the connection between GAN models, VAE models, and other techniques we learned before. Okay? All right, thank you very much.